Now in this video we will discuss Ostwald dilution law. What it tells us that this Ostwald dilution law illustrates that the Arrhenius concept for weak acids and weak bases was quantitatively explained by F.W. Ostwald by his Ostwald dilution law. So this is the main reason behind this. Now here for weak acids and weak bases, one thing is that they will not completely dissociate. So therefore Ostwald he has put forward his theory to explain the fraction of undissociated molecules by his theory, that is the factor alpha. That is he has differentiated how much that acid is dissociated and how much remains undissociated. So we will look forward for weak acid. Now look at the equilibrium of weak acid, that is Ha. I have already told this is nothing but what? Weak acid that exists in solution partly as a undissociated species Ha, means some fractions of Ha will remain in solution. You have to keep in mind this thing. And partly H plus and A minus ions. At the same time, both these ions, H plus and A minus ions, are means which are dissociated are present in solution. So this is equilibrium reaction for weak acids. Okay. So we have already seen in our last lecture, that is dissociation constant for weak acid and weak bases, that is Ka and Kb. So I have applied the dissociation constant Ka for this above reaction, that is weak acid. Okay. So what you will get? Ka is equal to concentration of product species, that is H plus and A minus, divided by the concentration of reactant, that is weak acid Ha. Now I have called this as the equation number 1 because this value I require for the next equation. So if we consider the equilibrium reaction of this weak acid, what I did here, I have divided into two parts, that is amount at equilibrium, and after that from this value I have determined the concentration at equilibrium. You have to keep in mind concentration term, we will look at afterward, but one thing you have to keep in mind, amount of fractions of ions which are remained at equilibrium. Now look at this Ha. As I have said in this explanation, some amount of ions, that is some amount of fraction of reactant molecules remains as it is. But at equilibrium, how much that concentration or how much that fraction which are remained at equilibrium, that we can determine with the help of this factor, that is 1 minus alpha. Okay. And the fractions of these two ions which are dissociated, how much dissociation is taking place, that is I have taken as a alpha. Means H plus which is dissociated, that fraction at equilibrium will be alpha, and A minus, the fraction which is present at equilibrium, will be alpha. So if I consider this as a alpha and alpha, so how much undissociated fraction of Ha will remain at equilibrium? It will be 1 minus alpha, because total minus how much that reactant is present at the end, that we can take their subtraction from 1. Okay. So this is the fraction which is remained at equilibrium, that is Ha, means which is not converted into product, which is remained as a reactant, that fraction will be 1 minus alpha. You have to keep in mind. Okay. After determining all these values, we can determine their concentrations, because for solutions we have to express all these fractions in terms of concentrations. So for that purpose, what I did, I have taken this factor, and when it will be divided by V, that is volume of solution, it will become concentration, because number of moles divided by volume of solution is nothing but concentration. As you know, this the simple or basic definition. So like that I did, I divided by the term V throughout the fraction values. So what I get, 1 minus alpha divided by V, alpha upon V, alpha upon V. Once you are able to understand this table, then you can determine the value of alpha in this Ostwald dilution law. Now we will look forward for the next step. Now we have to determine the value of Ka for this above equilibrium equation. So for that purpose, which values you have to know, that is equilibrium constant Ka for weak acids. You already know that equation. Ka is equal to concentration of H into concentration of A minus divided by concentration of Ha. This equation I have taken here. I have called that as the equation number 1, and in that case the concentration of all these terms you have to determine with the help of this table. So for that purpose I have written their specific values. Concentration of Ha is equal to 1 minus alpha divided by V, that you already determined here. That value you have to take there. And concentration of H as well as concentration H plus and concentration of A minus, both these values have the same value, that is alpha upon V. This value which comes from this table you have to keep in mind. Okay. So what I did, all these three concentration values I have substituted in this above equation number 1. So what you will get? You will get this value. Now here what I did, I solved this equation in simplified manner. I have represented here. You can look at alpha square upon V square, and this denominator terms I have reshuffled like this, V upon 1 minus alpha. Now here what I did, this V square and V get cancelled. Now what are the terms, which are the terms remainder that I have taken here as a Ka, that is what is remaining, alpha square divided by 1 minus alpha into V. These terms which I have got from the previous equation that I have represented here. And after that, for weak acids, this Ha term, that is alpha, is very small, that is the dissociated species, that is 1 minus alpha, it will becomes 1. Okay. That is the fraction of dissociated molecules for weak acids, it will become 1. Therefore we have to put this value in the equation, above equation, that is which we have determined just now only. So Ka becomes alpha square divided by 1 minus alpha. That alpha we have 1 minus alpha, we have considered it as a 1. Therefore by putting this value here, 1 into V, you will get V. Therefore Ka is equal to alpha square upon V, and Ka is this Ka, that is dilution constant for weak acids. We can also write in another form, that is in the form of concentration, for because you have to solve some different problems on this equation. So for that purpose, in some numericals you have given the values of volume as well as values of concentrations. According to that, you have to solve that problem. So in problem, when you are given the value of V, you can use this equation for the determination of K, and when they are in problem, when they give a value of concentration C, at that time you have to use this formula for the determination of dissolution constant of acid, and you can convert this above equation in the form of alpha, that is degree of dissociation. You can also determine by converting this equation into this form, that is only what you have to do here, you have to take the square root. By rearranging all these terms, you will get this equation, square root of K upon C, and here alpha, by taking again square root, you can reconvert that equation into another form, that is alpha is equal to square root of K into V in terms of V. So all this is about what we can say degree of dissociation. For the degree of dissociation, we have to make changes in the above equations. Okay, and one thing is that in this ionic equilibrium, on this Ostwald dilution law, there are many problems are present. You can solve the different equation, the different problems of different pattern. By solving all the numericals, you will get the maximum idea about this Ostwald dilution law.